Welcome everybody to our business math course. We are discussing today area between two curves. This is Magda Talib Al-Hinai from Sultan Qaboos University. So we want to find the area bounded by two curves. Let's start with the curve representing a function f of x. And we all know that the area under this curve, bounded by the curve f of x, the x-axis and the two vertical lines x equals a and x equals b, so mainly this area, we all know that this area is given by the definite integral of f of x dx from a to b. Now, suppose we have a function g of x, and we also want to find the area under g of x. Simple enough, this area under g of x is equal to the integral of g of x over dx from a to b. But now we're interested in the area between the f of x and g of x. We see that f of x is the upper curve and g of x is the lower curve. We are interested in this area. Yes, we can say that this area, which is shaded in red, it is equal to the area 1 under the green curve minus area 2 under the blue curve. Or simply we can write this. We substitute for area 1 and area 2, so we get this equation, which is equivalent to this. Or in other words, we can say that it is the area we are interested in, which is this part, is equal to the integral of from a to b over dx of the upper curve minus the lower curve, where here's the upper and here is the lower. Now let's see this example. Find the area bounded by the two curves x squared plus 1 and the other curve is minus x squared plus 9. So here we have the blue curve, which is x squared plus 1. This is a parabola which is shifted upwards 1 unit. And the green curve is also a parabola, but it is inverted and shifted upwards 9 units because we have a minus sign here, so it is open downwards. So this is the minus x squared plus 9 curve. Now we are asked to find the area bounded by these two curves. So we start our solution and we see that these two curves intersect at 2 points. These are the points of intersection. So we need to know the value of x at these 2 points so that we start our integration from this value of x to this value of x. So this is A and this is B. So when the two curves intersect at the point of intersection, we put x squared plus 1 is equal to minus x squared plus 9. And we solve for x. So we get 2x squared minus 8 equals to 0. Dividing both sides by 2, we get x squared minus 4 equals 0, which when solved, it gives us x is equal to plus or minus 2. So now we know that this is a vertical line x equals minus 2, and this is the vertical line x is equal to 2. Now, the area bounded by the two curves is the integral from a to b, which in our case is minus 2 to 2, upper minus lower, integration done with respect to x. So the upper curve, as we see, is the minus x squared plus 9, and the lower curve is the x squared plus 1. So we put integration from minus 2 to 2, the upper minus the lower. We do simplification and then we do integration. We integrate x squared with respect to x. It is x cubed over 3, and we integrate 8 with respect to x. So we get 8x. And we put our limits from minus 2 to 2, and I leave the rest for you to do on your own so that you get the numerical value of the area under consideration. Now let's see this example. We are asked to find the area bounded by the two curves y equals x, y equals root x, and the two vertical lines x equals 0 and x equals 2. So we start our solutions First of all, we graph the two curves. So we know that this is a straight line passing through the origin, and this is root x. We know the curve of root x. And we see that these two curves are intersecting in this point. The integral should be done from 0 to 2 because we want to find the area bounded between the two curves and the lines x equals 0 and x equals to 2. But let's have a look here. This is the area which we want to find. Actually, it's composed of two areas. The, let's call it area 1 and area 2. In area 1, which is dotted in pink, we see that the square root of x is the upper curve while the x is the lower curve. On the other side, this area which is dotted in yellow, we call it area 2. Here we have the straight line is now the upper while the root 2 is now the lower curve. Okay, so we need to find the point of intersection so that we find area 1 integrated from 0 to this point to this value of x, and then we continue integration from this value of x to 2. So the two curves, of course, we know that they intersect whenever we put them equal. So x is equal to root x will give us the points of intersection of the two curves. And we see that x is equal to root x implies that x is equal to 0 or 1. So here is the line x equals to 1. So we will perform integration from 0 to 1 to get area 1, and then we perform integration from 1 to 2 to get area 2. Then we add area 1 and area 2 to get the required total area. So here I see area is equal to area 1 plus area 2, where area 1 is the integral over x from 0 to 1, upper minus lower. Here we have the upper, as we said, is the root x, and the lower is the x. So root x is actually x power half. When we integrate it, it will become x power 3 over 2 over 3 over 2 minus the integral of x is x squared over 2, and then we substitute for the limits of integration 0 and 1. Okay, so here we get the answer to be 1 over 6. Next, we find area 2. Area 2 is the integral from 1 to 2 upper minus lower, integration being performed over x. So here we have the integral from 1 to 2. Upper is the straight line x, lower is the root x, and we perform integration term by term so that we get x squared over 2 minus x power 3 over 2 over 3 over 2, and the limits of integration are 1 and 2. We substitute for these two limits. We get the first when we substitute for every x by 2, and then we substitute for every x by 1. We continue simplification, and we then add the 1 over 6 to this amount, area 1 plus area 2, to get the total area we are looking. Now we move to an application of the area between two curves. This is the consumers and the producer surplus. Let's have a graph here. We put the demand curve and the supply curves. This is the demand curve. This curve indicates a relation between price and quantity. It gives us the price per unit at which consumers will purchase Q units, or say demand Q units. This one is the supply curve. This curve indicates the price per unit at which the manufacturer will sell or supply Q units. These two curves intersect at a point of equilibrium. At this point, when the supply is equal to the demand, we have market equilibrium. The coordinates of this point are Q naught and P naught. And here we say precisely at this unit, consumers will buy at the price P naught the quantity Q naught of product that producers wish to sell at the same price P naught. So this is the Q naught and this is the P naught. We notice that here are some consumers who are willing to pay more than the equilibrium price. And here are some producers who are willing to sell less than the equilibrium price. So this area above P naught, and which is bounded by the demand curve P node, this area, we call it the consumer's surplus. And we mean by the consumer surplus the total gain to consumers who are willing to pay more than the market equilibrium price. Now, let's see how can we calculate the consumer surplus. Suppose we have the demand function and we have it called f of q. The consumer surplus, and we give it the abbreviation CS, is given by the integral over q upper minus lower from 0 to q node. As I said, this gives the total gain of consumers who are willing to pay more than the equilibrium price. Now let's see the producer surplus. This part is the producer surplus. It is bounded by P node and the supply curve. And we calculate it in the same fashion. If we have the supply function, we call it GP. The producer surplus is given by this relation, which is again upper minus lower, P node minus G of Q, dQ. Integration is done over the interval from 0 to Q node. And also this gives the total gain of producers who will supply a product at a price less than equilibrium price. Now we see together the following example. For a certain item, the demand curve is given by P equals 20 over Q plus 1, while the supply curve is given by P equals 2Q plus 2. We're asked to find the equilibrium price and equilibrium quantity. Also, we are asked to find the consumer and the producer surplus. First, to find the equilibrium price and quantity, we need to put the supply equal to the demand because we know at equilibrium supply equals demand. And then we solve for Q to find the solution for Q, the values of Q. So this equation can be rewritten as the equation here. We multiply both sides by q plus 1, and we are sure that q plus 1 is not 0, so we're not multiplying by 0 by any ways. So here we start solving for q. We open the parentheses, so we get this quadratic equation, which has two solutions. One is minus 6 and the other is 3. So we reject any negative values because this is a quantity and the quantity cannot be negative. Okay, and then we take this value for Q to be 3, and we get the equilibrium price by plugging in this equation or this one, in either one. If you put Q equals 3, you will get price of equilibrium to be 5. Now, having found the equilibrium quantity and equilibrium price, we move to the second part of the problem to compute the consumer and the producer surplus. So the consumer surplus, we have the equation for it. It's the integral from 0 to Q node, equilibrium quantity, of f of q minus p node dq. Here we have the f of q. So we substitute for f of q and for p node and for q node, and we perform integration. We see that the first term here, when we integrate it, it's the logarithm of the denominator. The integral of this first term is the logarithm of the denominator, and the integral of minus 5 is minus 5q. So here we get 20 ln q plus 1 minus 5q, and we substitute for q by 3 and 0. We get this answer for the consumer surplus. For the producer surplus, we put the equation for it. We have a producer surplus is equal to the integral of P naught minus G of Q dQ, integral performed from 0 to Q naught. We have the Q naught and the P naught as we've seen. So we plug in their values. 0, we integrate from 0 to 3. Q naught is 3. And P naught, we put 5 for P naught, and G of Q is the supply function. We put its value is Q plus 2. And now we perform integration term by term. Of course, we see that 5 minus 2 is 3. The integral of 3 is 3q. And the integral of minus q is minus q squared over 2. We evaluate the integral from 0 to 3. So we get 4.5.